Now, in this lecture, we'll find out the area of a circle. In the drawing, we have quadrilateral ABCD. Inside this quadrilateral, we have this circle. We also know that side AB of this quadrilateral is equals to 2 units in its length, side BC equals to 8 units, and side DC also equals to 8 units in its length. In addition, we know that this is angle ABC that is equals to 90 degrees in its size. And this angle DCB equals to also 90 degrees in its size. Again, our mission is to find out the area of the circle. So first of all, we will do a construction. That is to say, we will extend side DA and side CB of this quadrilateral ABCD by a straight line until they touch each other. So actually, this is their touching point. We define their touching point as point M. We define this angle as theta. And we will focus on the right big triangle, triangle DCM. On the right big triangle, triangle DCM. This angle equals to 90 degrees, this angle equals to theta, therefore the missing angle here must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. BC is one side of quadrilateral ABCD, therefore it is absolutely a straight line. Then we extended the straight line BC by a straight line, and the result is CM. When you extend the straight line by straight line, the result is a straight line, therefore CM is also a straight line. If you focus on the upper side of the straight line CM at point B, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of CM at point B? We have this angle that is equal to 90 degrees plus the missing angle that is actually angle ABM. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. Therefore, the missing angle here must be equal to 90 degrees. In order to complete the sum of the angles on the upper side of CM at point B to 180 degrees, the missing angle here must be equal to 90 degrees. We will focus on the right triangle ABM. On the right triangle ABM, this is a right angle, this is equal to 90 degrees. This angle equals to theta, therefore the missing angle here must be equal to 90 degrees minus theta. Okay. In the next step, we prove that the big right triangle, triangle DCM, is similar to the small right triangle, triangle MBA. So I write it down. We prove that the big right triangle, triangle DCM, is similar to the right small triangle, triangle MBA. So why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. This is angle DCM in the big right triangle DCM. And it is equals to this angle that is actually angle ABM in the right triangle MBA. Repeat again. Angle DCM in the big right triangle DCM equals to angle ABM in the small right triangle MBA. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, it is a common angle that belongs to both triangles, so we can write down that angle theta equals to itself as a common angle that belongs to both triangles. So if we write to angle theta as it belongs to the big right triangle DCM, it will be called angle DMC, and it is equal to itself. If we relate to angle theta as it belongs to the small right triangle MBA, it will be called angle AMB. Repeat again. This equation means that angle theta equals to itself. We just call two angle theta two different names. So angle theta equals to itself as a common angle that belongs to both triangles. And finally, we have those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So this is angle MDC in the big right triangle DCM. And it is equals to this angle that is actually angle MAB in the small right triangle MBA. Repeat again. Angle MDC equals in the big right triangle DCM equals to angle MAB in the small right triangle MBA. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we can prove that all the three angles in the big right triangle DCM are correspondingly equal to all the three angles in the small right triangle MBA. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. The right big triangle DCM is similar. This is the sign of similar to the right small triangle MBA according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side DC is the big right triangle DCM over side AB in the small right triangle MBA equals to side CM in the big right triangle DCM over side BM in the small right triangle MBA. Hit again. We derive that DC over AB equals to CM over BM. DC is 8 here. DC equals to 8. over AB. AB is 2, and it is equals to CM. From the drawing, it is very easy to see that CM in total equals to CB plus MB. So CM equals to CB, that is 8, plus MB. So in total, CM equals to 8 plus MB. So we substitute CM here by 8 plus BM over BM. 8 over 2 is 4, so 4 equals to 8 plus BM over BM. Here we multiply this equation by BM, and we get that 4 times BM equals to 8 plus BM. So here we'll subtract BM from this equation, and we get that 4 BM minus BM is 3 BM, that is equals to 8. Here we divide this equation by 3, and finally we get that BM equals to 8 over 3 units in its length. BM equals to 8 over 3. So here we can write down the original drawing that this line segment BM equals to 8 over 3 units in its length. In the next step, we will focus on the right small triangle MBA, and we will implement the Pythagoras theorem on this small right triangle MBA. Here by PT is a version for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse on this small right triangle MBA is AM, therefore the square of the hypotenuse is AM squared, and it must be equal to AB squared plus BM squared. Repeat again, according to the Pythagoras theorem, in the small right triangle MBA, AM squared equals to AB squared plus BM squared. So AM squared, that is the square of the hypotenuse in the right triangle MBA, equals to AB squared. AB is 2, therefore AB squared is 2 squared, that is 4, plus BM squared. We just write down further that BM equals to 8 over 3, therefore BM squared is 8 over 3 squared. 8 over 3 squared is 8 squared, that is 64, over 3 squared, that is 9. So in total, 8 over 3 squared equals to 64 over 9. So AM squared equals to 4 plus 64 over 9. Here we multiply 4 by 9, and then we divide it by 9 in order to have a common factor with 64 over 9. And we get that AM squared equals to 4 times 9 is 36, so in total in the numerator we have 36 plus 64, all divided by 9. And 64 plus 36 is 100, so it is 100 over 9. So AM squared equals to 100 over 9. Here we take a root out of this equation, and finally we get that AM equals to the square root of 100 over 9. The square root of 100 is 10, and the square root of 9 is 3. So in conclusion, we found out that AM, the length of the hypotenuse AM, it is actually equals to 8 over 3 units. AM equals to 8 over 3 units. So I write it down in the original drawing. And here, AM, the hypotenuse AM equals to 8 over 3 units in its length. So in the next step we do another construction. That is to say, we draw perpendicular on side BC in such a way that the perpendicular will be also tangent to this circle. It is absolutely possible to do it. Why? Because you can draw the perpendicular on any point on BC. So we draw the perpendicular in a point that it will be also tangent to this circle. So first of all, this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular and BC as point T. We define the touching point of the perpendicular on BC. We define the touching point, we define the point of tendency of the perpendicular and this circle as point K. We'll extend the perpendicular TK until it touches side AD of quadrilateral ABCD. We'll define the touching point of the extended perpendicular TK at side AD as point L. By doing this construction, we created here the right big triangle, triangle LTM. In this big right triangle LTM, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus theta. Okay. In the next step, we define the center of this circle, this point as O. We define the point of tendency of tangent AB with this circle as point N. We define the point of tendency of tangent BT with this circle as point H. We join points O and H together by a straight line. Point O is the center of the circle, point H is the point of the circle itself, therefore OH is the radius of this circle. We define the radius of this circle as x, therefore OH equals to x because it is the radius of this circle. You can implement here rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. We have here as in the drawing a circle and tangent AB that is tangent to this circle at point M. Point M is the point of tendency. And you have the radius OM that is drawn to point M, that is to say it is drawn to the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule 1. You can implement rule 1 in our drawing. Why? Because in our drawing we have the radius OH that is drawn to point H. That is to say it is drawn to point H, that is the point of tendency of tangent BT with this circle. Whenever we have a radius that is drawn to the point of tendency, then tangent BT will be perpendicular to the reduced edge O. If BT is perpendicular to edge O, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, going to all 1. Likewise, we'll join points O and K together by a straight line. OK is the radius of this circle that's equal to x. The radius OK is drawn to point K, therefore according to all 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and N together by a straight line. ON is also the radius of this circle that is equal to x. According to our definition, the radius ON is drawn to point N, therefore according to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. In the next step, we'll focus on the small quadrilateral OH TK. In this quadrilateral OH TK, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus the missing angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees in its size. In order to complete the sum of the angles in this quadrilateral OKHT to 360 degrees, the missing angle here must be equal to 90 degrees. So actually, in this small right quadrilateral, quadrilateral OKHT, we have 4 right angles. And therefore, we can relate to this quadrilateral as a rectangle. It must be at least a rectangle if not a square, because it has 4 right angles. So, quadrilateral OKHT is a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle OKHT, side OK must be equal to the opposite side HT, but OK is x, therefore HT must be also equal to x in its length. Likewise, the opposite side OH must be equal to the opposite side KT in rectangle OKHT. But OH is x, therefore KT must be also equal to x. So we actually found out that in this quadrilateral OKHT is not a rectangle but a square. Why? Because all of its sides they are equal to each other. Each side of this quadrilateral is equal to x. Therefore, quadrilateral OKHT is a square. Likewise, we will repeat on the same process on this quadrilateral NB edge O. In this quadrilateral NB edge O, we have 1, 2, 3 right angles. Therefore, the fourth angle must be equal to 90 degrees. Therefore, we can relate to quadrilateral NOBH as a rectangle, and you know the opposite sides of a rectangle are equal to each other. That is to say, NO equals to the opposite side BH, but NO is x, therefore BH must be also equal to x. Likewise, according to the same rule, OH must be equal to the opposite side NB, but OH is x, therefore NB is also x. Again, we actually found out that quadrilateral NOBH is not a rectangle but a square. In conclusion, we found out that the length of this line segment BT equals to x plus x. So BT equals to 2x, so we can write here that BT equals to 2x units in its length. In the next step, we will prove that the big right triangle LTM is similar to the small right triangle MBA. So I write it down. We'll prove that the big right triangle LTM is similar to the small right triangle MBA. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So this is angle LTM in the big right triangle LTM. And it is equal to this angle in the small right triangle MBA. This is actually angle ABM. Repeat again, angle LTM in the big right triangle LTM equals to angle ABM in the small right triangle MBA. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle, it belongs to both triangles. So we can write down that angle theta equals to itself. It's a common angle that belongs to both triangles. So if we relate to angle theta as it belongs to the big right triangle LMT, it will be defined as angle LMT. And it is equal to itself. So if we relate to angle theta as it belongs to the small right triangle MBA, it will be defined as angle AMB. Repeat again. This equation means that angle theta equals to itself. We just call to angle theta two different names. Angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So this is angle MLT in the big right triangle LTM. And it equals to this angle, this is actually angle MAB in the small right triangle MBA. Repeat again. Angle MLT in the big right triangle LTM equals to angle MAB in the small right triangle MBA. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles in the big right triangle LTM are correspondingly equal to all the three angles in the small right triangle ABM. Therefore, we proved that the right triangle LTM is similar to the right triangle ABM according to angle similarity rule. So I write it down. The right triangle LTM, the right big triangle LTM is similar to the right triangle MBA according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side LT in the big right triangle LTM over side AB in the small right triangle MBA equals to side TM in the big right triangle LTM over side BM in the small right triangle MBA. Repeat again. We derive that LT over AB equals to TM over BM, and it is also equals to side LM in the big right triangle LTM over side AM in the small right triangle MBA. Repeat again. In conclusion, found out that LT over AB equals to TM over BM equals to LM over AM. So here LT is the missing side, so we will leave it as it is, over AB. AB equals to 2 units, therefore we substitute AB by 2. Here AB equals to 2. And it is also equals to TM. What is the length of TM? From the domain it is very easy to see. The Tm equals to Tb plus Bm. That is to say Tm equals to Tb, that is 2x, plus Bm, that is 8 over 3. So in total, Tm equals to 2x plus 8 over 3. Over Bm. Bm equals to 8 over 3. And it is equals to Lm. Lm equals to La plus Am. It is to say Lm equals to La plus Am, that is 10 over 3. So in total, Lm equals to La plus 10 over 3. So write it down. Lm equals to La plus 10 over 3, all divided by Am. Am equals to 10 over 3. So those two sides are equal to each other, therefore we get the first equation from those two sides that are equal to each other. So according to the first equation, LT over 2 is equals to 2x plus 8 over 3 over 8 over 3. So LT over 2 equals to, we have 2x plus 8 over 3. Here we multiply 2x by 3 and then we divide it by 3 in order to a common factor with 8 over 3. So in the numerator of this expression we will have 2x times 3, that is 6x, plus 8 divided by 3 and all divided by 8 over 3. In this side of the equation we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. After we cancelled 3, we left only with LT over 2, that is equals to 6x plus 8 over 8. Repeat again. We actually found out that LT over 2 equals to 6x plus 8 over 8. Here we cross multiply this equation and we get that x times LT equals to 2 times 6x plus 8. Here we divide this equation by 2 and we get that 8 over 2 is 4, so in this side of the equation we have in total 4LT. Is equals to 2 over 2 is 1, so in this side of the equation we have 6x plus 8. Here we divide this equation by 4, and finally we get that LT equals to 6x over 4 is 1.5x plus 8 over 4 is 2. So in conclusion, found out that LT equals to 1.5x plus 2. So here we can write down in the original drawing that this line segment LT equals to 2 plus 1.5x. LT equals to 2 plus 1.5x. We continue to focus on the long equation that we created here. We create equation number 2 from those two expressions that are equal to each other. So according to equation number 2, we have 2x plus 8 over 3 over 8 over 3. This is equals to LA plus 10 over 3 over 10 over 3. So this is the first equation that we created from the long equation. Here, in this side of the equation, we have 2x plus 8 over 3. So we'll multiply 2x by 3 and then we'll divide it by 3 in order to have a common factor with 8 over 3. So in the numerator of this expression, you will have 2x times 3, that is 6x, plus 8, divided by 3, and we have to divide it by 8 over 3. So here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled, and it is equals to LA plus 10 over 3. We multiply LA by 3 and then we divide it by 3 in order to have a common factor with 10 over 3. And we get that LA times 3 is 3 LA, so in total in the numerator we will have 3 LA plus 10 divided by 3 and all divided by 10 over 3. So here we have 3 in the numerator and 3 in the denominator, so 3 will also get cancelled. So what is left from this equation after we cancel 3 on both sides of the equation? In this side of the equation we left only with 6x plus 8 over 8. That is equal to, in the other side of the equation, we left only with 3 times LA plus 10 over 10. So here we'll cross multiply this equation and we get that 10 times 6x plus 8 equals to 8 times 3 times LA plus 10. Here we divide this equation by 2 and we get that 10 over 2 is 5, so it is 5 times 6x plus 8. That is equal to 8 over 2 is 4, so on the other side of the equation we have in total 4, and inside the brackets we have 3 LA plus 10. So here we'll open the brackets on both sides of the equation, and we will get that 5 times 6x is 30x, plus 5 times 8 is 40, so it is plus 40. That equals to 4 times 3 LA is 12 LA, and 4 times 10 is 40, so it is plus 40. So here we have 40 on both sides of the equation, so 40 will get cancelled, and we left only with 30x, that is equals to 12 times LA. Here we divide this equation by 12, and finally we get that LA equals to 30x over 12, that is actually 2.5x. So actually found out that the length of line segment LA is 2.5x units. Here, LA, line segment LA equals to 2.5x units in its length. In the next step, I will copy the small quadrilateral ALTB, this quadrilateral, with the circle that is described by this quadrilateral, and we will analyze this quadrilateral ALTB. So actually, this is quadrilateral ALBT that I copied from the original drawing. And we have a circle. The circle is inscribed by this quadrilateral, or the quadrilateral blocks this circle. We define the point of tendency of tangent AL with this circle as K. We define the point of tendency of tangent AB with this circle as L. We define the point of tendency of tangent LT with this circle as M. And finally, we define the point of tendency of tangent BT with this circle as N. We can implement here rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing we have a circle, and we have also the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. We can actually implement rule 2 in our drawing. Why? Because if we focus on the common external point, point A, From the current standpoint, point A, we have two tangents to this circle, tangent AL and tangent AK. And according to rule 2, they are equal to each other. That is to say, AL equals to AK, according to rule 2. So if we define the length of tangent AL as A, then AK must be also equal to A because they are equal to each other. In the next step, we will focus on the common standpoint, point B. From the common standpoint, point B, we have two tangents to this circle, tangent BL and tangent BN. And according to rule 2, they are equal to each other, that is to say, BL equals to BN. So if we define the length of tangent BL as B, then the length of tangent BN must be also equal to B because they are equal to each other. In the next step, we'll focus on the common standpoint, point T. From the common standpoint, point T, we have two tangents to this circle, tangent TN and tangent TM. And according to rule 2, they are equal to each other. This is to say, TN equals to TM. So if we define the length of tangent TN as C, then the length of tangent TM must be also equal to C because they are equal to each other. And finally, we focus on the common standpoint, point L. From the common standpoint, point L, we have two tangents to this circle, tangent LK and tangent LM. And according to rule 2, they are equal to each other. That is to say, LK equals to LM according to the same rule, rule 2. So if we define the length of tangent LK as D, then the length of tangent LM must be also equal to D because they are equal to each other. In the next step, we will add side AB to side LT. So we have AB, side AB, plus side LT. AB equals to A plus B, and LT equals to C plus D. So in total, AB plus LT equals to A plus B plus C plus D. In the next step, we'll join side AL to the opposite side, side BT. So AL plus BT. From the drawing, it is very easy to see that AL plus BT equals in total to A plus B plus C plus D. A plus B plus C plus D. So I actually found out that those two expressions, this expression and this expression, they are both equal to A plus B plus C plus D, therefore they are equal to each other. Okay? So we can write down that AB plus LT equals to AL plus BT. Repeat again, we actually found out that AB plus LT equals to AL plus BT. AB equals to 2 units in its length according to what is given as the question. So we substitute AB by 2 plus LT. We have already found out that this line segment LT equals to 2 plus 1.5x. So we substitute LT by 2 plus 1.5x. Repeat again. We substitute AB by 2 and we substitute LT by 2 plus 1.5x, and it is also equals to AL. We have already found out that AL equals to 2.5x, therefore we substitute AL by 2.5x plus BT. BT equals to x plus x, that is 2x. So we substitute BT by 2x. Yeah, substitute BT by 2x. So in conclusion, we found out that 2 plus 2 plus 1.5x equals to 2.5x plus 2x. 2 plus 2 is 4, so in total in this equation we have 4 plus 1.5x, that is equal to 2.5x plus 2x is 4.5x. So in conclusion, we found out that 4 plus 1.5x equals to 4.5x. Here we subtract 1.5x from this equation, and finally we'll get that 4 equals to 4.5x minus 1.5x is 3x. So 4 equals to 3x. Here we'll divide this equation by 3, and finally we will get that x equals to 4 over 3 units in its length. So we can find out that the radius x of this circle equals to 4 over 3 units in its length. Our mission is to find out the area of this circle. We know that the area of any circle is equals to pi times the radius square. If the radius is r, it is pi r square. So it is pi times the radius square. The radius of our circle is x, so it is pi x squared. It is pi and x is 4 over 3, and therefore x squared is 4 over 3 squared. So the area of our circle equals to pi times 4 over 3 squared. That is pi times 4 over 3 squared. 4 over 3 squared equals to 4 squared, that is 16, over 3 squared, that is 9. So in conclusion, we found out that the area of our circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equals to 5.585 square units. Repeat again. The area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equals to 5.585 square units. In the next step, I will summarize the lecture. In this lecture, we found out the area of this circle. In the drawing, we have quadrilateral ABCD. Inside this quadrilateral ABCD, we have a circle. In addition, we know that the length of side AB of quadrilateral ABCD equals to 2 units, side BC equals to 8 units in its length, and side DC equals to also 8 units in its length. This is angle ABC that is equal to 90 degrees in its size. And this is angle DCB that is also equal to 90 degrees in its size. It is a right angle. Again, our mission is to find out the area of this circle. In order to find out the area of this circle, we did a construction. That is to say, we extended side DA and side CB of this quadrilateral ABCD by a straight line, until they touch each other. This is their touching point. We define their touching point as M. By doing this construction, we get the right big triangle DCM. We define this angle as theta. So in the big right triangle DCM, this angle equals to 90 degrees, this angle equals to theta, therefore the missing angle here must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. Okay. Then CB is one side of quadrilateral ABCD, therefore it is absolutely a straight line. When we extended the straight line CB by straight line, the result is CM. And when you extend the straight line by straight line, the result must be a straight line. So CM must be a straight line. If we focus on the upper side of this straight line CM at point B, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equals to 180 degrees. So which angles we have at the upper side of CM at point B? We have this angle that is the right angle, that is equals to 90 degrees, plus the missing angle ABM. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. Therefore, the missing angle must be equal to 90 degrees. In order to complete the sum of the angles on the upper side of CM at point B to 180 degrees, the missing angle here must be equal to 90 degrees. If this angle equals to 90 degrees, it means that triangle ABM is the right angle. We focus on the right angle ABM. On the right angle ABM, this angle equals to 90 degrees, this angle equals to theta, therefore the missing angle here must be equal to 90 degrees minus theta. Okay? Then we proved that the right big triangle DCM is similar to the small right triangle MBA. Why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, it is a common angle that belongs to both triangles, so we can write down that angle theta equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. We actually proved that all the three angles of the right big triangle DCM are correspondingly equal to all the three angles of the right small triangle ABM. Therefore, those two right angles are similar to each other according to angle similarity rule. And from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We derive that side DC of the big right triangle DCM over side AB of the small right triangle ABM equals to side CM of the big right triangle DCM over side BM of the small right triangle MBA. I repeat again, we derive that DC over AB equals to CM over BM. DC is 8, AB is 2, and it equals to CM. What is the length of CM? From the dome it is very easy to see that CM in total equals to CB plus BM. That is to say CM equals to CB, that is 8, plus BM. So in total CM equals to 8 plus BM. Here, CM equals to 8 plus BM and over BM. So we found out that 8 over 2 equals to 8 plus BM over BM. 8 over 2 is 4, so 4 equals to 8 plus BM over BM. Here we multiply this equation by BM and found out that 4 times BM equals to 8 plus BM. We subtracted BM from this equation and found out that BM minus BM is 3BM. So 3BM equals to 8. 3BM equals to 8. We divided this equation by 3 and finally found out that BM equals to 8 over 3 units in its length. Here this line says that BM is equals to 8 over 3 units in its length. Then we focused on the right triangle in BM and we implemented the Pythagoras theorem on this right triangle in BM. According to the Pythagoras theorem in this right triangle in BM, AM squared equals to AB squared plus BM squared. Repeat again. in the right triangle MBA, according to the Pythagoras theorem, AM square equals to AB square plus BM square. So AM squared, that is the square of the hypotenuse, equals to AB square. AB is 2, therefore AB squared is 2 squared, that is 4, plus BM squared. We just write down further that BM equals to 8 over 3, therefore BM squared is 8 over 3 squared, that is 64 over 9. So in conclusion further that AM squared equals to 4 plus 64 over 9. Here we multiply 4 by 9 and then we divide it by 9 in order to overcome factor with 64 over 9. And found out that AM equals to 4 times 9 is 36 plus 64 divided by 9. 36 plus 64 is 100 divided by 9. So in conclusion we found out that AM squared equals to 100 over 9. We took a root out of this equation and finally found out that AM equals to the square root of 100 over 9. The square root of 100 over 9 is the square root of 100, that is 10, over the square root of 9, that is 3. So in total, AM equals to 10 over 3 units in its length. AM, the hypotenuse AM equals to 10 over 3 units in its length. Then we did another construction. That is to say, we drew perpendicular on side BC in such a way that the perpendicular on BC also will be tangent to this circle. Again, we drew perpendicular on BC in such a way that the perpendicular on BC will be also tangent to this circle. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. And point K is the point of tendency of the perpendicular on BC. Then we extended the perpendicular TK by straight line until it touches side DA in point L. By doing this construction, we created the right triangle LTM. In the right triangle LTM, this angle equals to 90 degrees, this angle equals to theta, therefore the missing angle here must be equal to 90 degrees minus theta. Then we defined the center of this circle as O, and we join points O and N together by straight line. OH is the radius of this circle. We define the radius of this circle as H, therefore OH is X. The radius OH is drawn to point H, that is the point of tendency of tangent BT with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BT will be perpendicular to the radius edge O. If BT is perpendicular to edge O, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Then we join points O and N together by straight line. ON is the radius of this circle that is equal to X. The radius ON is drawn to point N, therefore this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and K together by straight line. OK is the radius of this circle that is equal to X. The radius OK is drawn to point K, that is, therefore, according to rule 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. Then we focus on the small quadrilateral OKHT, this quadrilateral. In this quadrilateral, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 90 degrees times 3, 270 degrees. Plus the fourth angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore the missing angle here must be equal to 90 degrees. So inside quadrilateral OKHT we have 4 rectangles, therefore we can relate to quadrilateral OKHT as a rectangle. And you know that the opposite sides of a rectangle are equal to each other, that is to say OK equals to HT. But OK is X, therefore HT must be also equal to X. Likewise, OH must be equal to the opposite side KT in the rectangle OKHT. But OH is X, therefore KT must be also equal to X. So we actually found that quadrilateral OKHT is not a rectangle but a square. Why? Because all of the sides are equal to each other, each side equals to X. Then we repeated on the same process on this quadrilateral NOBH. In this quadrilateral NOBH we have 1, 2, 3 rectangles, therefore the fourth angle must be also equal to 90 degrees. Therefore this quadrilateral that has 4 angles, we can relate to this quadrilateral with 4 angles as a rectangle. And you know that the opposite sides of a rectangle are equal to each other. That is to say, side NO must be equal to the opposite side BH. But NO is x, therefore BH must be also equal to x. Likewise, OH, side OH must be equal to side NB in rectangle NOHB. But OH equals to x, therefore NB must be also equal to x. So actually found out that quadrilateral NOHB is not a rectangle but a square, because all of its sides are equal to each other. In conclusion, found out that BT in total equals to x plus x, that is 2x. Here, BT equals to 2x units in its length. Then we proved that the right big triangle LTM is similar to the small right triangle ABM. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle, it belongs to both triangles, so we can write down that angle theta equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees times theta, therefore they are equal to each other. So we actually proved that all the three angles of the right big triangle LTM are correspondingly equal to all the three angles of the small right triangle NBA. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that LT in the big right triangle LTM over AB in the small right triangle MBA equals to TM in the big right triangle LTM over BM in the small right triangle MBM, and it is equals also to LM in the big right triangle LTM over AM in the small right triangle MBA. And put again, we derive that LT over AB equals to TM over BM equals to LM over AM. LT is the missing side, so we leave it as it is, over AB. AB is 2, and it is equals to TM. What is the length of TM? From the drawing it is very easy to see that TM in total equals to TB plus BM. That is to say, TM equals to x plus 8 over 3. So TM in total equals to 2x plus 8 over 3. Here, Tm equals to 2x plus 8 over 3 over Bm. Bm equals to 8 over 3. Bm equals to 8 over 3. And it is equals to Lm. Lm equals to La plus 10 over 3. Again, Lm equals to La plus 10 over 3. And m equals to LA plus 10 over 3 over AM. AM equals to 10 over 3. Yeah. AM equals to 10 over 3. So in conclusion, we found out that LT over 2 equals to 2x plus 8 over 3 over 8 over 3, and it is also equals to LA plus 10 over 3 over 10 over 3. Those two sides are equal to each other, so we create a equation 1 that from those two sides, so those two expressions are equal to each other. So according to the first equation, we get that LT over 2 equals to 2x plus 8 over 3 over 8 over 3. So LT over 2 equals to 2x plus 8 over 3. We multiply 2x by 3 and then we divide it by 3 in order to overcome a factor with 8 over 3. So 2x times 3 is 6x, so in total, in the numerator of this expression, we have 6x plus 8 over 3 divided by 8 over 3. In this side of the equation, we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. After we cancel 3, we get that LT over 2 equals to 6x over 8, 6x plus 8 over 8. And repeat again, after we cancel 3, we found out that LT over 2 equals to 6x plus 8 over 8. Here we cross multiply this equation and found out that 2 times 6x plus 8 equals to 8 times LT. Here we divided this equation by 2 and finally found out that 8 over 2 is 4, so in this side of the equation we have in total 4 LT, 2 over 2 is 1. So inside, in total this side of the equation we have 6x plus 8. So 4 times LT equals to 6x plus 8. Here we divided this equation by 4 and finally found out that LT equals to 6x over 4 is 1.5x and plus 8 over 4. 8 over 4 is 2. So in total we found out that LT equals to 1.5x plus 2. Here LT in total equals to 2 plus 1.5x. Then those two sides that are equal to each other, so we created equation number 2 from those two sides that are equal to each other. So according to equation 2, we actually found out that 2x plus 8 over 3 over 8 over 3 equals to LA plus 10 over 3 over 10 over 3. So here we have 2x plus 8 over 3. We multiplied 2x by 3 and then we divided by 3 in order to overcome a factor with 8 over 3. 2x times 3 is 6x, so in total in the numerator of this expression we have 6x plus 8 divided by 3 and all divided by 8 over 3. And it is equals to LA plus 10 over 3. Here we multiplied LA by 3 and then we divided by 3 in order to overcome a factor with 10 over 3. So 3 times LA is 3LA. So in total, in the numerator of this expression, we have 3LA plus 10 divided by 3, all divided by 10 over 3. In this side of the equation, we have 3 in the numerator, 3 in the denominator, so 3 will get cancelled. In the other side of the equation, we have 3 in the numerator and 3 in the denominator, so 3 also will get cancelled. After we cancelled 3 on both sides of the equation, we left in this side of the equation only with 6x plus 8 over 8. On the other side of the equation we have 3LA plus 10 over 10. So we can find out that 6x plus 8 over 8 equals to 3LA plus 10 over 10. Here we cross multiply this equation and found out that 10 times 6x plus 8 equals to 8 times 3LA plus 10. Here we divided this equation by 2 and found out that in this side of the equation we have 10 over 2, that is 5, so in total this expression equals to 5. And inside the brackets we have 6x plus 8, that is equals to 8 over 2 is 4, so in total in this side of the equation we have 4 times 3LA plus 10. Then we open the brackets on both sides of this equation and finally found out that 5 times 6x is 30x. Plus 5 times s is 40, that is equals to 4 times 3LA, that is 12LA, and plus 4 times 10 is 40. So here we have 40 on both sides of the equation, so 40 will get cancelled, and we left only with 30x, that is equals to 12LA. Here we divided this equation by 12, and finally found out that LA equals to 30x over 12, that is 2.5x. So here LA, this 9/7 LA equals to 2.5x. Then I copied quadrilateral LABT with the circle that is described in it in the new page, and we analyze this quadrilateral LABT. This is quadrilateral LABT that I copied from the original drawing. We define the point of tendency of tangent LT with this circle as M. We define the point of tendency of tangent LA with this circle as K. We define the point of tendency of tangent AB with this circle as L. And finally, we define the point of tendency of tangent BT with this circle as N. And we have here rule number 2 that we can implement. If we focus on the common standpoint, point A, we have two tangents to this circle, tangent L and tangent AK. And according to rule 2, they are equal to each other. That is to say, LA AL equals to AK. AL equals to AK. So if we define AK is A, then AL must be also equal to A because they are equal to each other. So AL equals to AK equals to A. Then we focus on the common sum point, point B. From the common sum point, point B, we have two tangents to this circle. Tangent BL and tangent BN. According to rule 2, they are equal to each other. That is to say, BL equals to BN. Here, BL equals to BN, according to rule 2. So if we define one of those two tangents as B, then the other tangent must be also equal to B because they are equal to each other. And then we focus on the common sum point, point C. From the common sum point, point T, we have two tangents to this circle, tangent Tn and tangent Tm. And according to rule 2, they are equal to each other. That is to say, Tn equals to Tm. Tn equals to Tm according to rule 2. So if we define one of those two tangents as C, then the other tangent must be also equal to C, therefore, because they are equal to each other. So Tn equals to Tm equals to C. And finally, we focus on the common sum point, point L. For the common sum point, point L, we have two tangents to this circle, tangent LK and tangent LM, and according to rule 2, they are equal to each other. That is to say, LK equals to LM according to rule 2. So if we define one of those two tangents as D, then the other tangent must be also equal to D because they are equal to each other. So LK equals to LM equals to D. Then we join points AB and LT together. We had side AB. We add side AB to side LT in this quadrangle ALBT. Again, AB plus LT. What is the value of AB plus LT? AB plus LT, from the domain it is very easy to see that AB is A plus B and LT is C plus D. So in total, AB plus LT equals to A plus B plus C plus D. Then we join side AL to the opposite side, side BT in this quadrangle ALBT. So AL plus BT. AL plus BT, it is very easy to see from the domain that AL plus BT in total it is equals to A plus B plus C plus D. Again, AL plus BT also equals to A plus B plus C plus D. So those two expressions, they are both equal to A plus B plus C plus D, therefore they are equal to each other. That is to say, AB plus LT equals to AL plus BT. Okay. AB plus LT equals to AL plus BT. AB is 2 plus LT. What is the value of LT? LT equals to 2 plus 1.5x. LT equals to 2 plus 1.5x. If LT equals to 2 plus 1.5x, and it is equal to AL. What is the value of AL? AL equals to 2.5x. Here, AL equals to 2.5x plus BT. Here, BT equals to x plus x, that is 2x. So BT equals to 2x. So here, BT equals to 2x. So in conclusion, we found out that 2 plus 2 plus 1.5x equals to 2.5x plus 2x. 2 plus 2 is 4, so in total in this of the equation we have 4 plus 1.5x. That is equals to 2.5x plus 2x is 4.5x. So in total we actually found out that 4 plus 1.5x equals to 4.5x. Here we subtracted 1.5x from this equation and found out that 4 equals to 4.5x minus 1.5x is 3x. So 4 equals to 3x. Here we divided this equation by 3 and finally found out that x equals to 4 over 3 units in itself. Here, the radius x of this circle equals to 4 over 3 units in its length. And our mission is to find out the area of this circle. The area of any circle equals to pi times the radius squared. According to our definition, the radius of our circle is x, therefore the area must be equal to pi x squared. And x is 4 over 3, and therefore x squared is 4 over 3 squared. So pi x squared is pi times 4 over 3 squared. So the area of the circle equals to pi times 4 over 3 squared. 4 over 3 squared equals to 4 squared, that is 16, over 3 squared, that is 9. So in total, the area of the circle equals to either 16 pi over 9 square units, or in terms of numbers, the area of the circle equals to 5.585 square units. I repeat again, the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, the area of this circle equals to 5.585 square units. Okay, thank you very much.